Okay, good morning. Today I'm going to finish up or cover the theory for chapter 5, which is AC analysis. And then on Friday, we look at the example problems. Okay, so today we look at, let's see, phasors and complex impedances. And let's see, section 4. All right, so we stopped here. All right, any questions before I proceed? Okay. So sinusoidal, right? I said that AC analysis is also named as sinusoidal analysis. In this case, AC, of course, comprises of all kinds of shapes and waveforms: triangular, rectangular, pulse, sawtooth, and sinusoidal. But primary, we are going to look at just sinusoidal waveforms, mathematically represented with the sine and the cosine functions, right? So why sinusoidal? Well, the first and most important is that it's very easy to generate. You have a coil that is mechanically rotated inside a magnetic field. It passes through a magnetic north and a south pole. And so the shape of the the shape of the waveform that comes out is sinusoidal in nature. They are very easy to generate. The mathematical calculations are easier because the derivatives and the integrals of sinusoids, sine and cosine, are basically cosine and sine. And so sinusoidal waveforms are easy to handle mathematically, or easier to handle mathematically. And then, of course, again, mathematically speaking, any other waveform, whether it's rectangular, square, triangular, can be represented mathematically as a sinusoidal function, okay, through Fourier analysis. So again, sinusoidal is because very easy to generate and easier to handle mathematically. Now, the response of a circuit depends on the source. When we apply a DC source, we say that it's a DC circuit, and the response is also DC voltages and DC currents. If you apply an AC source to those same components, it becomes an AC circuit, and the response of the voltages and the currents is basically the AC steady state response. We do not have to solve any differential equations to obtain that steady state response. Okay. If you think back to chapters 3 and 4, voltage for an inductor, L di over dt. Current for a capacitor is C dV over dt, right? You can close the door. Yeah, okay. And so it's L di over dt or C dV over dt. And then chapter 4, we looked at how we can get a first order differential equation that we'd have to solve to obtain or to solve for transient analysis, right? So what we do is we actually, instead of doing all of that for AC, there is a method, mathematical method, whereby we can represent the sources and the components using complex number math. We represent them as complex quantities, and we use complex math to make the math less complex. Okay, we use complex number math to make the math simpler. And what happens is it reduces our circuit into simple circuit analysis problems. And we can apply the techniques that we learned in chapters 1 and 2 to AC analysis. All of the techniques. So we would not have to do this. We would not have to perform integration of VL to find the current for the inductor or the voltage for a capacitor. We would simply apply Ohm's law. Except the Ohm's law would now be using complex numbers. That's it. So we represented sources with phasors and inductors and capacitors with impedances. Okay, these are complex quantities represented using complex numbers. Sources are represented as phasors, and then Inductors and capacitors are represented with impedances. Resistors, as a reminder again, function the same for AC as they do for DC. So they do not change. All right. So the next two slides, we look at what phasors and what are impedances. Okay. The phasor is simply a vector that is rotating in the complex plane, and it's obtained using a phasor transform of the time varying expression, the time varying signal, which is shown right here. Okay. These phasors, unlike the ones from Star Trek, are not going to stun or kill you, but on occasion they will scramble your brains. So here we have the time domain representation. What happened to my pen? All right. Sorry about that. The computer in the classroom crashed, and so I was waiting.